You believe gravity is strong. You feel it every morning when you lift yourself out of bed, every time something slips from your hand and falls. It seems like the most powerful force in your life. But here is the truth. Gravity is the weakest force in the universe, embarrassingly weak. A tiny magnet can lift a paperclip against the pull of an entire planet. So, what is gravity at its core, and why is it so faint? Stay with me tonight, and the answer may quietly change how you understand your own weight. If this calms your mind, a soft like and subscribe helps these stories find others. Tell me, where are you, and what hour finds you? Let me bring you back into your own body for a moment. Feel the surface beneath you, whether it is a bed, a couch, a chair, or the floor of a quiet room. Something is pressing up against you right now, and you are pressing back down into it. You did not choose to do this. You are not flexing any muscle to make it happen. It is simply the condition of being alive on this planet. You are heavy. The world holds you, and in that holding, there is a kind of reassurance most people never stop to notice. Lift your hand for a moment. Just your hand. Feel the small effort it takes to keep it raised. Now, let it fall. Watch how it drops without hesitation, without negotiation, without the slightest delay. The earth claims it instantly. There is no force in your daily life more reliable than this. The sun may hide behind clouds. The wind may come and go. Your phone may freeze and your lights may flicker. But gravity has never failed you. Not once. Not for a single second of your entire existence. Think about how it shapes everything you do. The coffee in your morning cup sits flat and still inside its rim, held there by the invisible hand of the planet beneath you. The water from your tap arcs downward in a perfect, predictable curve. Your steps land where you expect them to land. When you sit down, you do not float gently into the seat. You drop, you commit. The world catches you every single time. This is why gravity feels enormous. It feels like a god of the everyday. It feels like the most powerful force you have ever known, because it is the one force you can never escape, never turn off, never even pause for a moment of relief. Astronauts who train for weightlessness describe the strangeness of it for years afterward. The body remembers gravity even when it is gone. The body expects to be held, and when nothing holds it, the body does not know what to do. So I want you to trust this feeling. Trust your own experience, because everything you are about to learn tonight depends on you first acknowledging just how powerful gravity seems from where you are sitting. It seems mighty. It seems like the foundation of the universe. It seems like the thing that built the mountains and the oceans and the orbits of the moons. And in a sense, you are right. Gravity did all of those things. Gravity does rule the cosmos at the largest scales. Gravity bends light, slows time, and crushes stars into pinpoints of impossible density. But here is where your story begins to crack. Walk over to your refrigerator. Or simply imagine it. There is almost certainly a small magnet on the door. Maybe it is shaped like a fruit, or a souvenir from a city you visited once, or just a plain colored disc holding up a photograph. It is small. It is unremarkable. It probably cost less than a cup of coffee. Now imagine taking that little magnet and bringing it close to a single iron nail resting on the floor. What happens? The nail jumps up. Stop and consider what just occurred. That tiny magnet, weighing perhaps a few grams, reached down and lifted the nail off the floor. And in doing so, it overcame the gravitational pull of the entire planet beneath your feet. A planet that weighs roughly 6 sextillion tons. That is a 6 followed by 21 zeros. A number so large that no human mind can hold it. The full weight of every ocean, every mountain range, every layer of molten rock pressing down into the core, every grain of sand on every beach, on every continent, all of it was pulling that nail toward the ground. And a magnet you could lose between the cushions of your couch defeated it instantly. Let that comparison breathe for a moment. Do not rush past it, because something in this picture is deeply, profoundly wrong with the way you have been thinking about gravity. If gravity were truly the mighty force, it feels like no magnet of any size could ever lift that nail. The entire planet should win. The planet should always win. It outweighs the magnet by a factor so enormous it cannot even be properly written on a normal piece of paper. And yet the magnet wins. The magnet wins every time. The magnet does not even strain. It does the job casually, effortlessly, as if the planet beneath it were barely there at all. So what is going on? What kind of force loses to a refrigerator magnet? What kind of fundamental pillar of reality is so feeble that a child's toy can shrug it off without trying? To understand the answer, you need to meet the other players. Because gravity is not alone in the universe. It is one of four. Four fundamental forces that shape every interaction in existence, from the spinning of galaxies down to the trembling of atoms. And gravity, the one you feel most, is the runt of the family. The weakest by an almost embarrassing margin. Let me introduce them to you one by one, slowly, carefully, because once you see them all together, the picture you carry of gravity will never fit the same way again. The first force is the strong nuclear force. You have never felt it in any direct way, and you never will, because it operates only within distances smaller than the nucleus of a single atom. But it is the reason matter exists at all. Inside every atom of your body, there are tiny particles called protons, crammed together in unimaginable closeness. Protons all carry positive electric charge, and positive charges repel each other furiously. Left to their own devices, the protons inside any nucleus would explode apart in an instant, ripping every atom in the universe into a useless mist of particles. But they do not. They hold. They hold because the strong nuclear force grips them with a fierceness that overpowers everything else. It is, as the name suggests, the strongest force we know. It is the glue that keeps the heart of every atom from flying apart. Without it, you would not be here. Your bed would not be here. The planet would not be here. There would be no planets, no stars, no anything. Just a faint static hum of disassembled fragments drifting through empty space. The second force is electromagnetism. This one you know intimately, even if you have never called it by name. Every time you flip a light switch, every time a screen glows in front of your eyes, every time your phone vibrates in your pocket, that is electromagnetism doing its work. It is the force that binds electrons to the nuclei of atoms, holding the structure of every molecule together. It is the force that makes chemistry possible, which means it is the force that makes life possible. The image you are seeing right now is electromagnetism delivering light from your screen into your eyes. The sound of my voice reaching your ears travels first through the same force. Every solid surface you have ever touched feels solid because of electromagnetism. When your hand presses against a table, you are not actually touching the atoms of the wood. You are feeling the electromagnetic repulsion between the electrons in your skin and the electrons in the surface. Everything you call contact is electromagnetism preventing collision. The third force is the weak nuclear force. This one is the quietest of the four, but no less essential. It is responsible for certain kinds of radioactive decay, the slow transformation of one type of atom into another over time. It is the reason the sun shines. Because deep inside our star, the weak force allows hydrogen to convert into helium, releasing the heat and light that warms your face on a summer afternoon. Without it, the sun would not burn. There would be no sunlight. There would be no warmth. There would be no growing seasons. The weak force is small in scale and slow in action, but it shapes the long unfolding of cosmic time. And then there is the fourth, gravity, the one you feel constantly, the one that holds your body to the surface of the planet, the one that drops the apple from the tree and pulls the rivers down to the sea. Surely this one, the only force you can perceive every waking moment, must be the giant of the four. It is not. It is not even close. To show you just how far from the truth that assumption is, I want to share some numbers with you. Numbers that physicists themselves still find difficult to fully accept because they describe a gap so vast it borders on the absurd. Compare gravity to the strong nuclear force. Gravity is approximately 10 to the 38th power times weaker. That is a 1 with 38 zeros after it. Try to picture a 38-digit number. You cannot. No one can. Compare gravity to the electromagnetic force. Gravity is roughly 10 to the 36th power times weaker. That is a 1 followed by 36 zeros. Compare gravity to the weak nuclear force. Gravity is around 10 to the 25th power times weaker. The smallest gap, and even this gap, is staggering beyond imagination. These ratios are so large that the human brain has no real way to grasp them. We are good at counting up to 100. We are passable at imagining 1,000. We can stretch our minds toward 1,000,000 if we squint. But 10 to the 36th power is not just a big number. It is a number that defies comparison with anything in ordinary experience. So let me try to translate it. Let me try to give you something you can hold in your hands. Imagine a single grain of sand, small enough to vanish between your fingers. Now imagine filling every beach on Earth with grains of sand, every coastline, every shore. Then imagine multiplying that by all the deserts in the world, the Sahara, the Gobi, the Atacama, every dune, every dry riverbed. Then keep multiplying. Multiply by every ocean floor coated in fine sediment. Multiply by every planet, every moon, every asteroid in our solar system, imagining each one ground into dust. Multiply by every star in the Milky Way, each one rendered into grains. Multiply by every galaxy in the observable universe. You are not even close. You would need to multiply that mountain of sand by itself many times over before you began to approach the kind of number that separates gravity from electromagnetism. The ratio is not a difference in scale. It is a difference in category. It is a chasm so deep that physicists have given the question of why it exists a special name. They call it the hierarchy problem, the mystery of why gravity sits so absurdly far below the other forces in strength. And yet here you are, sitting in your room, feeling held by the very force that loses to a refrigerator magnet, feeling the steady, undeniable weight of a planet whose pull is, in cosmic terms, barely a whisper. How can this be? How can the weakest force in the universe also be the one that feels the most present in your daily life? How can it be the one that built the planets, the one that sculpted the spiral arms of galaxies, the one that traps light at the edges of black holes? How can something so faint also be so dominant? The first answer, and the simplest, is reach. Gravity has something the other forces do not. It never cancels itself out. The strong force operates only inside atoms. The weak force does the same. Electromagnetism is powerful, but it comes in two flavors, positive and negative. And across large distances, these tend to balance each other into neutrality. A star is electrically neutral overall, because for every proton there is an electron. The forces inside it cancel. But gravity has no opposite. There is no negative gravity that pushes things away. Every speck of mass in the universe pulls on every other speck of mass, always attracting, always adding up, never cancelling. So although gravity is unbelievably weak per particle, it accumulates. It piles up. It adds itself together across trillions upon trillions of particles until the gentle whisper becomes a roar that holds moons in orbit and crushes the cores of stars. But this answer, satisfying as it sounds, only deepens the mystery, because it tells you how the weak force can become dominant at large scales. It does not tell you why the force itself is so absurdly weak to begin with. Why is the per-particle strength of gravity so feeble that it takes an entire planet to outdo a magnet you can hold between two fingers? Why did nature build the universe this way? Why is gravity, the architect of cosmic structure, also the most embarrassingly faint of all the forces that shape reality? This is where the textbook explanations begin to fall silent. This is where the simple answers run out. Because the truth is, no one fully knows. The greatest minds in physics, the ones who have stared at this question for decades, cannot say with certainty why gravity is so weak. They have ideas. They have theories. Some of them are beautiful. Some of them are strange. Some of them involve hidden dimensions of space curled up beneath the surface of reality, invisible folds where most of gravity's strength leaks away. Some of them involve particles we have never detected, particles so faint they may slip through every instrument we will ever build. Some of them suggest that gravity is not a fundamental force at all, but an echo of something deeper, an emergent ripple from the very fabric of information that underlies the cosmos. We will get to all of those ideas. We will sit with each of them in turn. But before we do, you need to feel the full weight of the puzzle. You need to carry it with you as we travel further. So, let me leave you here, at the edge of the first crack, with the question that will guide everything that follows. If gravity is the weakest force in the universe, why does it rule the largest structures we know? Why does it pull galaxies together across distances so vast that light itself takes billions of years to cross them? Why does it bend time, slowing the ticking of clocks near massive objects and speeding them up far from any planet or star? Why does it shape the very geometry of space, curving the empty void around every object that has ever existed? Why does it, of all the forces, refuse to behave like the others? The strong force, the weak force, and electromagnetism all fit neatly into a single theoretical framework, a beautiful structure called the Standard Model of Particle Physics. Gravity stands alone. Gravity refuses to join. Every attempt to weave it into the same equations has failed over and over for nearly a century. It is as if gravity belongs to a different language entirely, a tongue the rest of physics cannot translate. And yet it is the language your body speaks every second of every day, the weight in your shoulders, the settling of your chest as you exhale into your pillow, the slow, heavy pull of fatigue as the night deepens. This is the language gravity whispers, and you have been listening to it your whole life without ever asking what it really means. Tonight, we are going to ask. Tonight we are going to follow this question all the way to the strangest answers humanity has ever dared to consider. We are going to walk with a young man under an apple tree, watching fruit fall and asking whether the moon does the same. We are going to ride with a patent clerk in Switzerland as he imagines an elevator falling in empty space. And from that small thought experiment, we will pull out a new picture of reality so beautiful it still takes the breath of physicists 100 years later. We are going to descend into hidden dimensions. We are going to chase particles that may never let themselves be caught. We are going to stand at the edge of what is known and look out into what is not. And then, when the journey is done, we are going to return here, to this room, to this bed, to this body of yours that feels so heavy and so held, and we are going to look at that weight with new eyes. Because by the time we are finished, you will understand that what you feel right now, the steady, undeniable pull of the earth beneath you, is not what you think it is. It never was. The answer is stranger than any textbook ever told you, stranger and quieter, and somehow more tender than the word force could ever capture. So, settle in. Let your breathing slow. Let your body sink a little deeper into whatever is holding you. The journey is long, and the night is generous, and the cosmos has been waiting patiently for you to ask the right question. The first crack has opened. Let us follow it down. To understand how strange the modern answer is, you first need to understand the picture it replaced. And to understand that picture, we need to travel back in time. Not far, just a few centuries. To a small farmhouse in the English countryside on a warm afternoon in the year 1666. The plague was loose in London. The great universities had closed their doors. Students had been sent home to wait out the sickness, and one of those students was a quiet, intense young man of 23. His name was Isaac. He had been studying at Cambridge, but now he was back at his mother's farm in the village of Woolsthorpe, with little to do and far too much time to think. He was a strange young man even then, solitary, watchful, the kind of person who could sit perfectly still for hours, staring at nothing in particular, while his mind churned through ideas no one around him could follow. The orchard behind the farmhouse was old and quiet, apple trees in long, uneven rows. The kind of trees that drop their fruit slowly through the late summer, one apple at a time, each one landing in the grass with a soft, heavy thud. Isaac liked to sit out there. The house was full of family and noise, and the orchard offered something the house could not. Silence, space, room for a young mind to wander. Picture him there, the afternoon light slanting through the leaves, a book resting on his knee, half forgotten, his thin face turned upward, watching the sky between the branches, the air smelling faintly of grass and ripe fruit, and somewhere above him an apple loosening from its stem. You know what happens next. Everyone knows. The apple falls. It does not fly sideways. It does not drift up toward the clouds. It does not hover politely in the air waiting for instructions. It drops straight down toward the center of the earth, just as every apple has ever done, and just as every apple ever will. Most people, witnessing such a thing, would not even notice. They would brush it aside, or pick it up and eat it, or set it down on the grass without a second thought. But Isaac was not most people. Isaac watched the apple fall, and as it fell, something began to turn over in his mind. A question so simple a child could ask it, and yet so deep that no one in human history had ever fully answered it. Why did the apple fall down? Why not sideways? Why not up? What was pulling it? And here is where his mind made the leap that would change the world. Isaac lifted his eyes from the fallen apple in the grass, and he looked up, past the branches, past the leaves, all the way up into the deepening sky, where the moon was already showing itself faintly in the late afternoon blue. And he asked the question no one had thought to ask before. What if the same thing pulling the apple is pulling the moon? Stop for a moment and feel the size of that thought, because you are so used to it now that it sounds obvious. But in 1666, this was not obvious. This was nearly heretical. For thousands of years, going back to the ancient Greeks, people had believed that the heavens and the earth were made of different stuff and obeyed different rules. The earth was the realm of falling apples, of muddy roads, of decay and change. The heavens were the realm of perfect circles, eternal motion, divine geometry. The moon did not fall. The moon did not behave like apples. The moon was something other. But Isaac, sitting in his orchard, dared to imagine that the wall between earth and sky was not a wall at all. He dared to imagine that the same invisible hand which tugged the apple from the tree might also be tugging the moon as it circled the earth. He dared to imagine that the universe was not divided into two realms, one earthly and one heavenly, but united by a single law that governed everything from a falling fruit to a hanging celestial body. If he was right, the implications were staggering. It meant that gravity was not a property of the Earth alone. It meant that gravity was everywhere. Every rock, every river, every cloud, every star, every planet, all of them pulling on each other, drawn together by some invisible thread woven through the fabric of existence. He could not test the idea right away. He needed mathematics he did not yet have. He needed years of work. He needed to invent, almost from scratch, the mathematical language we now call calculus, simply because no existing tool was sharp enough to describe what he was thinking. But the seed was planted that afternoon in the orchard, the seed that would grow into the most influential scientific idea of the next 2 centuries. When Isaac finally published his work, 21 years later, in a book called the Principia, the world received it with stunned silence, followed by slow rising awe, because what he had done was almost unimaginable. He had taken the entire heavens and the entire earth and bound them together with a single equation. One equation. To describe the falling of apples and the orbiting of moons and the wheeling of planets and the slow march of comets. One equation written in a language he himself had invented that could predict the motion of nearly anything in the universe. The law he gave us is breathtakingly simple. So simple that you can understand it tonight, lying in your bed, without ever having taken a physics class. Let me walk you through it gently. Every object that has mass pulls on every other object that has mass. That is the heart of it. Read it again. Every object that has mass pulls on every other object that has mass. Not just Earth pulling on apples, not just the sun pulling on planets. Every object. The teacup on your nightstand is pulling on you right now. You are pulling on it right back. The book on your shelf is pulling on the wall across the room. The wall is pulling on the book. Every speck of matter in the universe reaches out invisibly and tugs at every other speck. There is no exception. There is no escape. Mass calls to mass. The strength of the pull depends on 2 things. First, it depends on how much mass each object has. The more mass, the stronger the pull. A pebble pulls weakly. A boulder pulls more strongly. A mountain pulls more strongly still. A planet pulls so strongly that everything on its surface stays glued to it. A star pulls so strongly that entire planetary systems orbit around it. The more mass, the louder the call. Second, it depends on how far apart the objects are. The closer they are, the stronger the pull. The farther apart, the weaker the pull. And not just weaker in a gentle, gradual way. The weakening is steep, double the distance, and the pull becomes only 1/4 as strong. Triple the distance, and the pull becomes 1/9. The force fades quickly with distance, like the warmth of a candle as you back away from it. That is it. That is the law of universal gravitation in plain language. Mass attracts mass. More mass means more pull. More distance means less pull. 3 sentences, 3 simple ideas, and from those 3 sentences, the entire dance of the cosmos can be calculated. To feel why this was so revolutionary, imagine 2 ships drifting on a perfectly calm sea. The water is glass smooth. There is no wind, no current, no oar in the water, no sail catching breath. Just 2 ships sitting quietly on the surface, a few hundred meters apart. According to Newton, those ships would slowly, almost imperceptibly, begin to drift toward each other. Not because of any wind, not because of any current, simply because they have mass, and mass calls to mass. Given enough time and a perfectly still sea, those 2 ships would eventually touch hulls. They would be pulled together by the invisible hand of gravity. The same hand that pulled the apple, the same hand that holds the moon, the same hand that arranges the planets around the sun. This idea was beautiful in a way that earlier ideas had never been. It was simple, It was universal. It applied everywhere, to everything, all the time. And most astonishingly of all, it worked. The predictions it made came true with eerie accuracy. Astronomers used Newton's law to calculate the orbit of the moon, and the calculations matched what they saw in the sky. They used it to predict the motions of the planets, and the planets obeyed. They used it to predict tides, the slow rhythmic rising and falling of the seas, and the math poured out the right answers for every coast, every harbor, every day of the year. Then came one of the greatest triumphs in the history of science. A friend of Newton's, an astronomer named Edmund Halley, took the law of universal gravitation and used it to study the path of a particular comet that had appeared in the sky in the late 1600s. Halley noticed something. Records of earlier comets showed a similar path appearing roughly every 76 years. He wondered if all of these might be the same comet, returning again and again on a long, lonely orbit around the sun. If Newton's law was correct, Halley reasoned, then this comet should come back at a predictable time. He calculated when, and he died before the answer arrived. But on Christmas night, in 1758, decades after Halley's death, the comet returned, exactly as Newton's law had predicted. A single equation had reached forward through time and pulled a celestial body out of the future, placing it precisely where the mathematics said it would be. The world saw, with sharp new clarity, that the universe was not a mystery beyond reach. It was a machine, a vast, glorious, mathematical machine, and humans had just figured out how to read its gears. Newton's law became the foundation of everything that followed. Engineers used it to build bridges. Sailors used it to navigate the seas. Astronomers used it to discover entirely new planets, planets no one had ever seen, simply by noticing that the orbits of known planets were being subtly tugged by something invisible. They calculated where the hidden body must be, pointed their telescopes at that exact patch of sky, and there it was. Neptune, discovered in the year 1846, was found not by accident, but by mathematics. The law of universal gravitation had pulled a planet out of the darkness simply by predicting where it must be. For 2 centuries, this picture reigned. It seemed perfect. It seemed final. It seemed as if Newton had reached into the heart of nature and pulled out one of its deepest secrets. Generations of physicists assumed that the foundation was now laid, and that all future work was simply a matter of polishing the details on top of it. And yet, there was always one strange thing, one quiet, unsettling thing that even Newton himself could not explain. He had described how gravity acted. He had not described what gravity was. His law told you exactly how much one mass pulled on another. It told you how the pull changed with distance. It told you how to predict orbits, tides, falling apples, returning comets. It did all of this with stunning precision, but it never answered the simpler, deeper question. What is the pull? What is doing the pulling? What is reaching across the empty space between 2 objects and dragging them toward each other? Think about how strange that is. The sun is 93 million miles from the Earth. There is nothing in between. Empty space, cold and vast. And yet somehow, across that emptiness, the sun is reaching out and grabbing the Earth, holding it, swinging it through a vast circular path year after year, never letting go. By what means? Through what invisible thread? There is no rope, there is no chain, there is no contact of any kind, and yet the grip is unbreakable. Newton himself wrestled with this. He could not pretend the puzzle was not there. In private letters to his colleagues, he admitted, in his own careful 17th century language, that the idea of one body pulling on another at a distance through empty space, without any medium between them, was an absurdity that no thinking person could fully accept. He suspected there must be some hidden mechanism behind it, some reason the force could travel across the void. But he could not say what that mechanism was. He could only describe the behavior, not its cause. He wrote that he framed no hypotheses about it. He simply reported what gravity did and let the deeper question remain open. This was, in its way, an extraordinary act of humility. Newton was the most celebrated thinker of his age. He could have invented an explanation and dressed it in mathematics, and most of his contemporaries would have accepted it without question. But he refused. He said, in essence, that he had described the phenomenon but had not understood it. The how was clear, the why was not. So the picture Newton left behind was a strange one. It was triumphant and incomplete at the same time. Gravity worked. The math was perfect. The predictions were uncanny. And yet at the center of it all sat a question no one could answer. What is this invisible pull? What is doing the pulling? How does it cross empty space? For 200 years, that question stayed open. Not because people stopped asking it, but because no one could find a better answer than the one Newton had given. The mathematics was simply too good. It worked too well. To improve on Newton, you would not just need a new idea. You would need to overturn the very foundation he had laid, while still preserving all of the predictions that foundation had so beautifully made. That seemed impossible. So the question lay quiet. The picture endured. Apples fell, moons orbited, comets returned on schedule, and the world settled into the comforting certainty that gravity, whatever it might be, was now understood. But there were small cracks, tiny, almost invisible cracks that only the most careful observers could see. The planet Mercury, the closest world to the Sun, did not quite orbit the way Newton said it should. There was a tiny wobble in its path, a small, slow drift that no calculation based on Newton's law could fully erase. It was easy to ignore, easy to write off as measurement error, but the wobble was real. The cosmos was whispering something, and no one yet could hear what it was saying. 2 centuries passed. Generations of physicists came and went. The world built telegraphs, then telephones. Steam engines gave way to electric ones. Cities grew vertical. The face of civilization changed almost beyond recognition. And through all of it, Newton's law stood at the center of physics, untouched, undefeated, the unshakable foundation of the modern understanding of the universe. Until a quiet young man in Switzerland, working a modest job at a patent office in the city of Bern, began to daydream about elevators. He was not a famous professor. He was not part of any prestigious laboratory. He was a clerk. His job was to review patent applications submitted by inventors, reading their technical drawings, deciding whether the ideas had merit. He did this work carefully, but it did not occupy all of his mind. There was always room left over, room for thoughts that wandered far past the patent office walls. In his off hours, this young clerk thought about light. He thought about time. He thought about what would happen if you could ride alongside a beam of light at its own impossible speed. And he thought, in a way that no one before him had ever quite thought, about what it would feel like to fall. What would it feel like, he wondered, to be inside an elevator whose cable had suddenly snapped? The elevator and everything inside it, you included, plunging down through space together. If there were no windows, if you could not see the floors flashing past, would you even know you were falling? Would you feel any pull at all? Or would you feel exactly the same as if you were floating motionless in deep empty space, far from any planet or star? It was a small question, almost childish in its simplicity, but the more he turned it over in his mind, the more he realized that it pointed towards something enormous, something that would not just refine Newton's picture of gravity, something that would shatter it entirely and rebuild it into a form so strange and so beautiful that nearly every physicist alive today still finds it almost unbelievable. His name was Albert Einstein, and the dream he was about to dream would change everything you have ever felt about your own weight. The orchard in Woolsthorpe had given the world an apple. The patent office in Bern was about to give the world something far stranger. A new way of seeing gravity, a new way of seeing space, a new way of seeing time itself. But that is a story for the next part of the night. For now, let the comfort of Newton's world linger a little longer. Feel the weight of your body on the bed, and imagine it as Newton imagined it. A simple pull, a clear, invisible hand, the mass of the earth calling gently to the mass of you through some quiet, unexplained reach across empty space. It is a tender picture. It is the picture that built the modern world, and it is the picture you have carried in the back of your mind for your entire life. In a moment, we will begin to take it apart, but not just yet. Let it rest with you a little longer. Let yourself feel held by the old story, the way the old story held humanity for 2 long, peaceful centuries. The cracks are coming. The clerk in Bern is already dreaming. The elevator is already falling. But for now, you are simply here, in your bed, with the apples and the moon and the comet, and the calm, slow drift of 2 ships on a windless sea, all of them pulled together by the same quiet hand that no one yet has dared to name. Let us return to that quiet patent office in Bern. The year is 1907. The young clerk we left at the end of the last part is sitting at his wooden desk, surrounded by stacks of paper. Patent applications, diagrams of new clocks, sketches of electrical devices. The work is steady, modest, unglamorous. He earns enough to support a small family. He is 28 years old. He has no laboratory. He has no expensive equipment. He has no team of assistants. He has only a pencil, some paper, and the inside of his own head. But the inside of his head is on fire. Albert Einstein had a particular kind of mind. He could not always sit still with formulas the way other physicists could. He needed pictures. He needed scenes. He needed to imagine himself inside the problem, walking around it, touching its edges, watching how it behaved from different angles. He called these little mental movies thought experiments. Most of them never made it onto paper. They unfolded silently in his imagination while he stamped patent forms with one hand and let his mind wander far past the office walls with the other. On this particular afternoon, the daydream that came to him was simple, almost embarrassingly simple. He pictured a person standing inside an elevator, an ordinary elevator, the kind that carries people up and down inside a tall building. Steel walls, a small light overhead, maybe a handrail along one side. Nothing unusual at all. Then, in the daydream, the cable snapped. The elevator dropped. Not gently, not slowly. It fell freely, all at once, plunging downward through the empty shaft. And inside that falling elevator, the person Einstein had imagined was falling too, falling at exactly the same speed as the floor beneath their feet, falling at exactly the same speed as the air around them, falling at exactly the same speed as every loose object inside the cabin. Einstein closed his eyes and asked himself what that person would feel. Picture it with him. You are inside the falling elevator. The cable has just broken. You did not see it happen because there are no windows. But suddenly, something has changed. Your feet, which were pressing firmly against the floor a moment ago, no longer press against anything. Your weight is gone. The familiar heaviness in your shoulders has lifted. Your hair, which had been hanging quietly along your neck, drifts upward as if you were underwater. The coins in your pocket float gently out into the air around you. The keys on your belt rise up and hover at eye level. You yourself are no longer standing. You are drifting, suspended, held by nothing, pulled by nothing. There is no sound except the soft rush of air, and even that is gone if the elevator is sealed. Now, Einstein asked himself, here is the question. You are inside this windowless elevator. You cannot see outside. You do not know whether the cable has snapped or not. You only know what your body is telling you, and what your body is telling you is that you feel completely weightless. Could you, from inside the cabin, tell whether you are falling toward the earth or floating motionless in deep, empty space, light years from any planet or star? He thought about it for a long time. He turned it in every direction, and he came to a conclusion so simple and so devastating that it would unravel 200 years of certainty about the nature of gravity. No, you could not tell. There is no experiment you could perform inside that elevator that would distinguish between the two situations. You could let go of a pen, and the pen would hover in the air beside you. That is exactly what would happen in deep space, far from any gravitational pull. You could throw a ball gently across the cabin, and it would travel in a perfectly straight line. That is exactly what would happen in deep space. You could measure your own weight on a scale, and the scale would read 0. That is exactly what would happen in deep space. Inside the cabin, there is no difference. None. 0. Falling freely toward the earth feels identical to floating in the void. Stop and let that settle, because most people, when they first hear this, brush past it as a curiosity. They nod and move on. But Einstein did not move on. He sat with this little observation the way a jeweler sits with a strange new stone, turning it under the light, looking for hidden facets. And as he turned it, he began to see something that no one before him had seen. If falling under gravity feels exactly the same as floating in empty space, then maybe, just maybe, gravity is not what we have been told it is. Maybe gravity is not a pull at all. Maybe what we call gravity is something far stranger, something hiding inside the very geometry of the world. Let us slow down here, because this is the moment everything changes. This is the hinge of the entire night. If you take only one idea away from this entire script, let it be this one. For Newton, gravity was a force, an invisible reaching hand that stretched across empty space and tugged objects toward each other. The earth pulled on the apple, the sun pulled on the planets. Mass called to mass, and the call traveled silently across the void. For Einstein, gravity was not a force at all. Read that line again. Gravity is not a force. When you let an apple drop, nothing is pulling it. There is no invisible hand reaching up from the ground to grab it. There is no tug. There is no rope. There is no pulling of any kind. The apple is simply moving through the natural shape of the world around it. And the natural shape of the world around it, near a large body like the Earth, happens to curve gently downward. So the apple, with nothing else to do, follows that curve. It rolls along the slope of reality itself, like a marble rolling along the inside of a smooth bowl. The Earth is not pulling the apple. The Earth is bending the space around itself, and the apple is simply going where the bent space goes. If you have never heard this before, you may need to read those last lines a second time, or a third. Most people did. The first physicists who encountered Einstein's idea sat in stunned silence for days. Some of them refused to believe it. Some of them spent the rest of their lives trying to disprove it and failing, because what Einstein had done in the quiet of his patent office was nothing less than redraw the foundations of reality. To understand the picture he was offering, you first have to understand a strange new word: spacetime. For most of human history, space and time were thought of as two completely separate things. Space was where things existed. Time was how things changed. They felt independent. You could move through space by walking across a room. You could move through time by simply sitting still and waiting. Two different stages on which the drama of the universe played out. Einstein said no. They are not two stages. They are one stage, a single woven fabric, 3 dimensions of space and 1 dimension of time, all bound together into a single 4-dimensional weave. Every point in this weave is not just a place, it is a place at a moment. To exist anywhere is to exist somewhere at some time. There is no separating them, they are stitched together at every thread. This single fabric is what physicists now call spacetime, and it is everywhere. It is the medium in which everything you have ever experienced takes place. The room you are in right now is not just sitting in space. It is sitting in space-time. Your body is not just moving through the seconds of the night. It is moving along a path through this woven structure, a path that has length in the spatial directions and length in the time direction at once. Now picture this fabric stretched out before you. It is not made of cloth. It is not made of rubber. It is not made of any physical material at all. It is the structure of reality itself. But for the purposes of imagining it, let us pretend it is a vast, flat sheet, stretched perfectly smooth, extending in every direction further than you can see. That is what empty space-time looks like in a place far from any matter, flat, calm, featureless. Now place a heavy object onto that sheet, not a metaphor for an object, the actual object, the earth, for instance. What happens? The fabric bends. It does not break. It does not tear. It simply dips downward, forming a wide, gentle hollow around the earth, the way a heavy ball would press into a stretched trampoline. The deeper you get toward the center, the more steeply the fabric curves. Out at the edges, the curvature fades back toward flatness. This is the picture Einstein offered. Every massive object in the universe presses into the fabric of space-time and warps the geometry around it. Every star is a deep well. Every planet is a softer dip. Every moon is a gentler dimple. Even you, your body, your bones and breath, are pressing the tiniest possible warp into the space-time around you right now. The warp is unimaginably small because your mass is so small, but it is there. You are quietly bending reality just by existing. And here is where the new picture takes the place of the old one. Slowly, carefully. Let me place them side by side so you can feel the difference. In Newton's world, when an apple falls, the earth reaches up with an invisible hand and pulls it down. Mass calls to mass across empty space. There is a pulling, there is a tugging, there is a force. In Einstein's world, when an apple falls, nothing reaches up at all. The earth has simply carved a deep curve into the space-time around it. The apple, hanging from its stem, is balanced on the edge of that curve. When the stem releases, the apple is no longer being held in place. It does the most natural thing in the universe. It rolls along the slope, into the well, toward the center of the curve, down toward the planet beneath. There is no force. There is only geometry. There is no pull. There is only the natural shape of the world. What if nothing is pulling you toward the earth right now? What if every moment of your life, the weight you have felt in your shoulders, the heaviness of your tired body at the end of a long day, the pull of the floor against your feet, what if none of that has ever been a force at all? What if you have been rolling your whole life along the gentle slope that the earth has carved into the fabric of reality? What if gravity is not a thing the universe does to you? What if gravity is the shape the universe has, and you have simply been moving the way that shape requires? This is what Einstein saw, sitting in that patent office in 1907. He did not have all of the equations yet. Those would take him another 8 years of brutally hard work to finish. But the picture was there. The vision was clear. Gravity is not a force in the world. Gravity is the curvature of the world itself. When the full mathematical theory was finally completed in 1915, Einstein gave it a name. He called it general relativity, and it made predictions that no other theory had ever made. Predictions so strange that even Einstein himself was nervous about them. He predicted that light, which has no mass at all in the ordinary sense, should still bend when it passes near a heavy object. Because light, like everything else, has to travel through the curved fabric of space-time. And if the fabric is curved, the path of light has to curve with it. In 1919, just 4 years after he finished his theory, an English astronomer named Arthur Eddington sailed to a small island off the coast of Africa to test this prediction during a total solar eclipse. During the eclipse, the moon would briefly block out the sun, allowing astronomers to see the stars sitting just behind it. Einstein's theory said that the light from those stars, passing close to the sun on its way to Earth, should bend slightly because of the sun's enormous mass curving the space-time around it. Newton's theory said the bending should be much smaller, almost negligible. When Eddington's photographs were developed and measured, the answer came back like a quiet thunder. The stars were not quite where they should be. Their light had bent by exactly the amount Einstein predicted. The sun, simply by existing, was warping the space-time around itself, and the light of distant stars was rolling along that warp like a stream of water finding its way around a stone. The headlines of the world's newspapers the next day all said the same impossible thing. Einstein was right. The universe was not what anyone had thought. Space and time were a fabric, and the fabric could bend. Now, bring all of this back to your own body. Right now, in your bed, settle deep into the mattress, the weight of your shoulders, the heaviness of your legs, the pull of the pillow against the back of your head. What is happening here? In the old picture, the planet is reaching up with a great invisible hand and pulling you downward. The bed is pushing up against you, holding you in place against that pull. Two forces, locked in balance, keeping you exactly where you are. In the new picture, nothing is pulling you at all. You are simply sitting at the bottom of a curve that the Earth has carved into space-time. Your natural path, the one your body wants to follow if nothing interferes, is to roll deeper into that curve, to fall, to plunge toward the center of the planet. That is what your body is trying to do, every single second, without effort, without exception. Your body wants to fall, but the mattress is in the way. The mattress, with all of its springs and fibers and stitched fabric, is not letting you fall. It is holding you up, not in the sense of fighting against a force that wants to pull you down, but in the much stranger sense of physically blocking your natural motion through curved space. The mattress is pushing you upward, away from the path you would otherwise take, away from the path you are still trying to take, right this moment, with every ounce of your being. The chair beneath you, if you are sitting in one, is doing the same thing. The floor beneath the chair is doing the same thing. The bones in your feet, if you are standing, are doing the same thing. Read this slowly. The chair is not holding you up against gravity. The chair is pushing you out of your natural path through curved space. The floor is not stopping you from being pulled down. The floor is interrupting your fall. Falling is the default. Standing still is the strange thing. This is, I think, one of the most quietly beautiful and quietly unsettling realizations a human mind can have. Everything you have ever called weight is the sensation of being prevented from falling. Every time you feel heavy, you are feeling something blocking you. A mattress, a chair, a pair of boots, the skin of the earth itself. None of these objects are pulling you. They are stopping you. They are intercepting the smooth, natural roll of your body along the geometry of the world. Imagine for a moment that the floor beneath you suddenly disappeared. Not just the floor, the entire planet. Every layer of rock and metal and molten core, all of it, gone in an instant. What would happen to you? You would not fly up. You would not drift sideways. You would simply continue along your natural path through space-time. And because the Earth would no longer be there to curve the fabric, that path would suddenly become straight. You would coast through the void at a steady speed, in a perfectly straight line, never accelerating, never decelerating, simply moving along the now flat geometry around you. The pull would be gone. Because the pull was never a pull. The pull was the bending. And without the planet there to bend it, the bending would smooth itself out, and you would be free. This is what astronauts experience in orbit. They are not weightless because they have escaped gravity. They are weightless because they are falling freely. The space station they live in is plunging toward the Earth at every moment, but it is moving sideways so quickly that it keeps missing the surface, looping around the planet in an endless, graceful fall. Inside the station, the astronauts are rolling along their natural paths through curved space with nothing intercepting them. No mattress, no floor, no chair. They feel weightless because, in the deepest physical sense, they are. The sensation of weight comes only from being blocked. Take away the blocking, and the weight vanishes. What does this mean for you lying in your bed? It means that every familiar sensation of heaviness in your body tonight is, in truth, the gentle pressure of the world refusing to let you fall. You are not being pulled into the bed. You are being prevented from passing through it. The mattress, that ordinary object made of cotton and foam, is the one thing standing between you and the slow, steady roll of your body toward the center of the Earth. And the only reason any of this is happening is because the Earth has bent the fabric of reality just enough to create the curve you are now sitting in. The Earth, in its quiet, enormous mass, has pressed itself into space-time and shaped a soft valley around its surface. You are in that valley. You have always been in that valley. Every step you have ever taken has been a step along its slope. Every fall, every stumble, every casual descent of an object from your hand, every one of them has been an expression of the simplest law in this new picture of reality. Things move along the geometry of the world. That is gravity. That is all of it. There is no pull. There is no hand. There is only shape. And yet, even with this beautiful new vision, the original puzzle still has not been answered. We have changed the picture of gravity completely. We have replaced an invisible force with a curved geometry. We have shown that falling is the default, and that weight is just resistance to the natural shape of reality. But we have not yet explained why the curvature itself is so absurdly gentle. We have not explained why the fabric bends so faintly. We have not explained why a refrigerator magnet can defeat the warping of an entire planet. Einstein gave us the shape. He never told us why the shape is so soft. He showed us the geometry. He never told us why the geometry barely flexes. That mystery is still waiting, and in the next part of the night, we will pick it up again. We will sit with the strange consequences of this curved world. We will see time itself bend. We will watch clocks slow down. We will look into the deepest curves of all, the ones we now call black holes, and we will move closer, step by step, to the question that has been waiting for us since the first crack opened. But for now, lie still. Feel your body settled in its small, private valley. The earth beneath you is not pulling. It is simply shaped. And you, like every apple before you, like every moon, like every star, are quietly resting in the curve it has made. I know what has just happened to your mind. I have been quietly pulling at the corners of your understanding for the last hour, and the picture you walked in here with no longer fits the world you are looking at. The floor is no longer holding you up against a pull. The bed is no longer cradling you against a force. The chair beneath you has become a strange device for blocking your natural fall through the geometry of reality. This is a lot. I know it is a lot. So before we go any deeper, before we descend into the stranger consequences of this new picture, let me give you something to hold on to. A simple image, a place to stand, a way of seeing curved space-time that you can carry with you through the rest of the night. Imagine a large rubber sheet, the kind you might find stretched across an old garden trampoline or pulled taut between four wooden posts in a science classroom. The sheet is smooth and flat, wide enough that you can walk around it, strong enough to hold a fair amount of weight without tearing. Picture it stretched perfectly level in front of you, the surface humming faintly with tension, ready for something to be placed on it. Now, take a small marble, a tiny glass sphere, no bigger than the tip of your thumb. Roll it gently across the surface. What happens? The marble travels in a straight line. It rolls evenly from one edge of the sheet to the other, without veering left or right, without slowing or speeding up. The path it takes is the most natural path on a flat surface, a clean, straight line. This is what motion looks like in empty space-time. Far from any star, far from any planet, far from any object of any significance, the fabric of reality lies perfectly flat. Anything moving through it travels in straight lines. Nothing pulls, nothing curves, nothing complicates the journey. Now reach for something heavier, a bowling ball, or a heavy iron sphere if you prefer. Lift it carefully and set it down in the very center of the rubber sheet. The sheet sags. Watch how it bends around the ball. The fabric dips downward, forming a smooth circular hollow that grows steeper toward the middle and softer toward the edges. The deepest part of the curve is directly beneath the ball itself. The shallowest part is far out at the rim, where the dip fades back into flatness. The whole sheet has been reshaped. It is no longer level. It has been deformed by the simple presence of mass. Now, take that small marble again. Roll it across the sheet. But this time, instead of aiming straight, send it past the heavy ball at a slight angle. Send it in a path that would, on a flat sheet, miss the ball entirely. Watch what happens. The marble does not travel in a straight line. As it approaches the edge of the curved region, the slope of the dip begins to influence its motion. It starts to lean inward. It curves. The closer it comes to the heavy ball, the more steeply it bends. If you have given it just the right speed, it will not fall all the way to the center. It will swing around the heavy ball in a long, graceful loop, rising back up the far side of the curve, before falling back down again and beginning another orbit, around and around. The marble has begun to circle the heavy ball, not because anything is reaching out and pulling it, but because the very shape of the surface it is rolling on has changed. This is the picture, in miniature, of the entire solar system. The sun is the heavy ball. The planets are the marbles. The rubber sheet is space-time. The Earth, the moons, the comets, all of them are rolling along the slopes of the great curved valley that the sun has pressed into the fabric of the cosmos. Their motion looks like orbiting only because they are caught on the inside of a shape they cannot escape. They are not being pulled. They are simply going where the geometry leads them. For most people, when they first encounter this picture, something quietly clicks. The strangeness of the previous part begins to settle. You can almost see it now. The Earth carving its small dip. The moon circling within that dip. Your own body, sitting at the bottom of its tiny, personal hollow, resting on whatever surface refuses to let it slide deeper. This is a wonderful picture. It is the picture most physics teachers use. It is the picture that appears in countless videos, illustrations, and textbooks. It is one of the most successful visual metaphors in the history of science communication. And it is wrong. Not entirely wrong, but wrong in a particular and important way. And I have to tell you why. Because the rubber sheet picture, beautiful as it is, hides one of the deepest oddities of what Einstein actually discovered. Look at the rubber sheet again. Look at how it works. The bowling ball sags into the sheet because something is pulling the ball downward. The marble curves toward the ball because the dip in the sheet is sloped downward, and something is pulling the marble in that downward direction too. The entire mechanism of the rubber sheet, the way it bends, the way the smaller balls roll inward, the way the orbits form, all of it depends on the existence of a gravitational pull beneath the sheet. There has to be some outside force pulling things downward into the dip, otherwise the bowling ball would not sag in the first place. The marble would not roll toward it. The whole demonstration would simply float there, motionless and uninstructive. So the rubber sheet metaphor uses gravity to explain gravity. It depends on the very thing it is trying to describe. It is a useful picture, but it leans on a hidden assumption that the real universe does not need. The real space-time fabric needs no outside pull. There is no downward direction beneath the universe. There is no greater gravity below all of reality, calling the cosmic ball into a deeper dip. The bending of space-time around a massive object is not a sagging into anything. The fabric is not draped over anything. It does not need to be. The bending is intrinsic. It is part of the geometry itself. Mass simply causes the surrounding space-time to be shaped that way, with no external force required to make it happen. This is one of the most difficult things to truly absorb. The rubber sheet shows you a curve in a familiar way, with up and down and a sagging weight. The real curve has no up and no down. It just is. The space around a star is genuinely warped in 3 full dimensions, with time itself woven into the warping. There is no view from outside. There is nothing the fabric is dipping into. The curvature is the universe. So the rubber sheet is a helpful first picture, the kind of image that lets your imagination get its footing. But carry it gently. Hold it as a temporary stepping stone, not as the final truth. Behind it lies something stranger, a curvature that is not draped over anything, a shape that bends without falling, a geometry that exists in its own right, independent of any larger framework holding it up. Now, with that gentle warning in place, let us begin to walk into the consequences, because once you accept the central idea, that mass curves space-time, an avalanche of strange and beautiful predictions begins to unfold from it. Predictions that have been tested again and again in the century since Einstein first wrote them down. Predictions that have come true every single time. Here is the first one. And it is the one that quietly stuns most people the first time they truly grasp it. Time runs slower near massive objects. Read that line carefully. Time itself, the steady ticking forward of 1 second after another, slows down when you are deep inside a curve in space-time. It does not feel slower from inside. To you, your seconds still feel like seconds. Your heart beats at its normal pace. Your clocks all seem to tick at their normal speed. But if you were to compare your clock, after a long stretch of time, to a clock placed far away from any massive object, the 2 clocks would no longer agree. The one near the mass would have ticked fewer times. Less time would have passed for it. You would have aged, just slightly, less than the person far above you. This is not a metaphor. This is not an illusion. This is a measurable, experimentally verified fact about the universe. Imagine you place one identical atomic clock at the base of a tall mountain, deep in a valley, and another identical clock at the summit, high above. The clock in the valley is closer to the center of the Earth. It sits deeper inside the curve in space-time that our planet has carved. The clock at the summit is slightly farther from the center, slightly higher up the slope of that curve, slightly closer to flatness. Leave both clocks running for years, then bring them together and compare them. The clock in the valley has ticked fewer times than the clock at the summit. The difference is tiny. We are talking about billionths of a second per year, but the difference is real. Engineers who design global positioning satellites have to account for this exact effect every single day. The satellites, orbiting far above the Earth in much weaker curvature, experience time slightly faster than the receivers on the ground. If the engineers ignored this effect, the position calculations that your phone relies on would drift off by miles within hours. The fact that your map applications can guide you turn by turn through unfamiliar cities is, in a quiet way, a daily confirmation that Einstein was right. Time bends with the geometry. The closer you are to mass, the slower it flows. Astronauts who spend long stretches on the International Space Station return to Earth slightly younger than they would have been if they had stayed on the surface, not in any way you would notice. We are talking about fractions of a second over months of orbit, but the difference is measurable. Their bodies have ticked through fewer seconds of existence than yours has, simply because they were sitting in a slightly shallower part of the Earth's curve. Pause and feel what that means. Time, the most reliable companion you have ever had, the steady drumbeat that has accompanied every breath of your life, is not the same everywhere. It is shaped by the geometry around it. Down here, in the gentle bowl of the Earth's space-time, time flows just slightly slower than it does up there, near the satellites. Right now, as you lie in your bed, time is flowing a fraction more slowly for you than for someone on the top of a skyscraper. Not enough to feel, not enough to matter for any practical purpose in your life. But it is happening. The universe is treating you and that distant person to slightly different rates of time. The fabric of reality is making sure of it. Now move on to the second consequence. Light bends around massive objects. We touched on this in the previous part, when we mentioned Eddington's eclipse expedition in 1919. The moment when starlight passing close to the sun was found to have curved by exactly the amount Einstein had predicted. That single observation toppled 2 centuries of certainty and made Einstein a global household name. But the story did not stop there. In the decades that followed, astronomers learned to use this effect as a tool. They discovered that very massive objects, like enormous galaxy clusters, can bend the light of even more distant galaxies behind them so dramatically that the distant galaxies appear distorted, smeared into arcs and rings around the closer mass. We call this gravitational lensing. The universe itself acts like a vast irregular lens, magnifying and warping the light of objects far beyond. Without curved space-time, this effect would not exist. With it, the lensing is everywhere, visible in nearly every deep image our telescopes have ever taken. Now think of the picture. Light, the fastest thing there is, the thing that never slows down, the thing that cuts cleanly through empty space at nearly 300,000 kilometers every second, still has to follow the contours of the universe. Even light bends, not because anything is pulling on it. Light has no mass for gravity to pull. Light bends because the path it travels is curved. Space-time decides where the path leads, and light, like everything else, simply goes where the path goes. Now we come to the most extreme consequence, the deepest curve, the place where the geometry stops being gentle and becomes terrifying. Black holes. A black hole is not a hole. The name is misleading. There is no opening in space, no tunnel, no entrance into another world. A black hole is something stranger. It is a region of space-time where the curvature has become so steep, so absolute, that no path leads back out. Inside that region, every possible direction of motion leads further inward. There is no up. There is no out. There is no escape. The geometry itself has folded so deeply that even light, the swiftest traveler in the universe, cannot climb back to the surface once it has fallen below a certain boundary. That boundary is called the event horizon. It is not a wall. It is not a barrier. It is simply the line at which the slope becomes too steep ever to return from. Let us bring this back to our rubber sheet picture, with all its imperfections still in place. Earlier, We imagined a heavy bowling ball pressing down into the sheet, creating a smooth circular dip. That was our Earth, or a small star. Now imagine something far heavier. Imagine taking an entire warehouse full of bowling balls and somehow squeezing them into a single dense lump. Then drop that lump onto the sheet from a great height. The sheet does not just dip. It tears down into an almost vertical well. The walls of the well grow steeper and steeper, plunging downward at a near impossible angle. Any marble that strays too close to the edge has no chance of escaping. It tumbles inward, accelerating, vanishing into the darkness. The real black hole is far stranger than even this. There is no actual hole in space-time. There is only curvature so extreme that every path leads inward. The center of a black hole is not a place you can visit. It is a place where the geometry itself breaks down, where the equations of general relativity stop giving meaningful answers, where physicists themselves admit that we do not yet fully understand what is happening. And here is something to sit with. These objects exist. They are not theoretical curiosities. They are real. We have seen them. In 1919, Einstein's curved spacetime was an idea. By the late 20th century, astronomers had found dozens of likely black holes scattered across the galaxy. In 2019, an international team of scientists released the first ever direct image of a black hole, a dark circular silhouette ringed by glowing gas, sitting at the heart of a galaxy, 55 million light-years away. The picture was blurry. It was orange and shadowed and far from sharp, but it was a black hole, photographed by humanity. The shape that Einstein had described in equations was now staring back at us from a telescope. The contrast between the curve around our Earth and the curve around a black hole is staggering. The Earth presses into space-time the way a small pebble presses into a trampoline. The dip is gentle, the slope is soft. Things roll into it slowly, taking long, lazy paths around the planet, taking days or weeks or years to complete a single orbit. A black hole, by contrast, presses into space-time the way a wrecking ball might tear into the same trampoline if dropped from the height of an aircraft. The fabric does not just dip, it plunges. It nearly snaps, and anything caught in that plunge is gone forever. And yet, even with all of this, even with curved space-time, bending light, slowing clocks, and black holes that swallow stars, even with one of the most successful theories in the history of physics, even with experimental confirmations stretching across more than a century, even with all of this beauty and all of this strangeness packed into one elegant idea, the original mystery is still there. Why is the curvature so faint? Why does it take an entire planet to press a tiny dip into the fabric of reality? Why does it take an object the mass of the sun to bend the path of a beam of light by just a sliver of an angle? Why does it take something as monstrous as a black hole, with the mass of many millions of suns crushed into a single point, to make the curvature steep enough to truly impress itself on the universe? Why does the fabric of space-time resist bending so stubbornly? Why is the geometry so reluctant to flex? If you imagine that fabric as a real material, then it is a material of almost unimaginable stiffness. To bend it even a little, you have to gather enormous amounts of mass. The Earth, 6 sextillion tons of solid rock and metal, bends space-time just enough to keep us on its surface. The Sun, 330,000 times more massive than the Earth, bends it enough to hold the entire solar system. To create a black hole, you need to compress an enormous amount of mass into a space smaller than the original object should ever be able to occupy. The fabric does not want to fold. It wants to lie flat. It bends only when forced, and even then, only stubbornly. This is what gives gravity its weakness. Not a weak pull, a reluctant geometry. The reason a refrigerator magnet can lift a nail against the gravitational pull of the Earth is, in this new picture, the reason a small magnetic dimple in the electromagnetic field can outshape the gentle curve that an entire planet has been able to coax out of the spacetime around it. Mass simply does not have very much grip on geometry. Even 6 sextillion tons only gets you a dip soft enough that a child's toy can lift things out of it. Einstein gave us the geometry. He showed us how the bending works. He gave us equations of staggering beauty that describe exactly how mass and energy carve the shape of the universe around them. His theory has passed every test, every prediction, every experiment. For more than 100 years, no observation has ever contradicted it. It is one of the most successful theories ever produced by the human mind. But he never told us why the geometry barely flexes. He never told us why this particular fabric, the one our universe happens to be woven from, resists bending so completely. He never told us why mass has such a weak influence on shape. He never told us why gravity, in its essence, is so unimaginably gentle. He gave us the rules of the game without telling us why the rules were tuned this way and not some other way. This is the deeper question. This is the question that has haunted physicists for the last 100 years, even as they have celebrated the success of general relativity, even as they have used it to discover black holes and gravitational waves and the expansion of the universe itself. Beneath every triumph, this question has been quietly waiting. Why is the bending so soft? Why is gravity so faint? And in the next part of the night, we are going to walk straight into the strangest answers physicists have ever offered. Answers that involve hidden dimensions of space, curled up too small to see. Answers that involve particles too quiet ever to detect. Answers that suggest gravity might not even be a real fundamental thing at all, but a kind of echo, a shadow, an emergent ripple from something far deeper than space and time themselves. But that is for the next part. For now, you can rest in the beauty of the picture we have built. The fabric is bent, the clocks are slowed, the light is curved, the orbits dance along the slopes, and you, lying in your bed, are sitting at the bottom of a small soft hollow in the geometry of reality, gently pressed into the curve by the planet beneath you. The geometry holds you, the geometry shapes you. The geometry, for all of its weakness, has built the entire cosmos around you. The mystery is still alive, the deeper answer is still waiting, and the night is far from over. We are about to step past the edge of what is known. I want you to feel that. Up until this moment in the night, everything I have told you has been settled science. Newton's law has been verified for centuries. Einstein's geometry has been tested for more than 100 years. Falling apples, orbiting moons, bending light, slowed clocks, black holes photographed by telescopes. All of it confirmed, all of it solid, all of it sitting on a foundation so well examined that no working physicist alive today doubts any of it. But the question we are about to ask has no settled answer. We are walking into the most active frontier of modern theoretical physics, into ground that is still shifting beneath the feet of the people who study it for a living. The very smartest minds on this planet, the ones who have devoted their entire lives to understanding gravity, do not know why it is so weak. They have ideas. They have beautiful, strange, sometimes breathtaking ideas. But they do not know. And I am going to tell you the truth about that, because the honesty is part of the wonder. So slow down with me. Settle a little deeper into your bed. The next part of the journey requires patience and stillness, because the answers are partial, and the questions are the kind that humans have been asking for a very long time without quite resolving them. There is a name physicists give to the puzzle at the center of tonight's story. They call it the hierarchy problem. It is one of the deepest open questions in all of theoretical physics. And it is not really one question, but a family of related questions, all circling the same strange fact about our universe. Why is gravity so absurdly far below the other forces in strength? Why is there such a vast empty gap between the gravitational realm and the other three? Why does the universe seem to be sorted into a hierarchy, with gravity sitting alone at the very bottom, separated from its siblings by ratios so enormous that no one knows where the separation came from? When you look at the other three forces, the strong nuclear force, the electromagnetic force, and the weak nuclear force, they all sit within a few orders of magnitude of each other. Their strengths differ, yes, but they live in the same neighborhood. They are not identical, but they are close enough that physicists can fit them into a single theoretical framework called the Standard Model of particle physics. The Standard Model is one of the great triumphs of human thought. It describes the behavior of every known elementary particle and every known fundamental interaction, except for gravity. It has been tested to extraordinary precision. Every particle it predicted has been found. Every interaction it described has been verified. It is, by almost every measure, the most successful scientific theory ever produced. But gravity is not in it. Gravity has never fit. Every attempt to weave gravity into the Standard Model has run into walls that no one has been able to climb. The mathematics simply refuses to cooperate. When physicists try to describe gravity at the same scales where the other forces operate, at the tiny scales inside atoms and below, the equations explode. They produce nonsense. They produce infinities. They produce predictions that disagree with everything we know about how the universe behaves. This is not a small problem. This is, perhaps, the single largest unsolved problem in fundamental physics. For nearly 100 years, brilliant people have tried to build a theory that joins gravity with the other forces into one unified picture, and for nearly 100 years, they have failed. Not for lack of trying, not for lack of intelligence. For some deeper reason that no one yet understands, gravity refuses to play with the others. It stands apart. It speaks a different language. And nowhere is its strangeness more obvious than in the question of its weakness. So how have physicists tried to explain it? What are the leading ideas? Tonight, I want to walk you through three of them. Three of the most influential, most discussed, most argued over attempts to answer the question we have been circling all night. Why is gravity so faint? The first idea is one of the strangest. It suggests that gravity is not actually weak at all. It suggests that gravity is, in its true form, just as strong as the other forces, but that we, in our ordinary three-dimensional experience, are only seeing a small piece of it. The rest of gravity, the bulk of its strength, is leaking away into dimensions of space that we cannot see. Read that again. Dimensions of space that we cannot see. There are more dimensions than the three you are familiar with, and gravity, unlike the other forces, can travel through all of them. This is the idea of extra dimensions. And to understand it, you have to first stretch your sense of what space itself can be. You know three dimensions intimately, up and down, left and right, forward and backward. These are the three directions of space that you have been moving through your entire life. Every object you have ever encountered exists in three dimensions. Every room you have ever stood in has a height, a width, and a depth. The world you live in is solidly, comfortably, three-dimensional. But what if there were more? What if, hidden inside every point in space, there were additional directions, curled up so tightly that they are too small for any human instrument to detect? Imagine a long, thin garden hose stretched out across a field. From a great distance, the hose looks like a one-dimensional line. You can only move along it in one direction, forward or backward. That is all. But if you walk up close to the hose, you suddenly see something else. The hose has thickness. It has a second dimension that was invisible from far away. A tiny insect crawling on the surface of the hose can move not only forward and backward along its length, but also around its circumference. The hose, which looked one-dimensional from a distance, is actually two-dimensional up close. The second dimension was always there. It was just curled up too small to see. This is the picture physicists have been exploring for decades. They suggest that the universe might have more than 3 spatial dimensions, but that the extra ones are curled up at scales so unimaginably small that we have no direct way to perceive them. They might be curled at scales billions of times smaller than an atom. They might be tucked into every single point in space, invisible to every measurement we can currently make, and yet very much there. Now here is the strange and beautiful part. The other 3 fundamental forces, electromagnetism and the 2 nuclear forces, can only travel through the 3 large dimensions of space that we experience. They are confined to the surface of our ordinary 3-dimensional world. They cannot enter the hidden extra dimensions. Gravity, in this picture, is different. Gravity can spread out through all of the dimensions. It is not confined, it leaks. It spills outward into the hidden directions, dispersing its strength across a much wider stage than the other forces have access to. If this is true, then the gravity we feel is only the small portion that remains within our 3 large dimensions. The bulk of its strength is invisible. It has spread out into the hidden dimensions where we cannot detect it, where it does nothing observable to our world. What we experience as weak gravity is actually full-strength gravity diluted across far more space than we know about. Picture it this way. Imagine you are holding a flashlight in a small room. The light from the flashlight illuminates the wall in front of you brightly. Most of its energy reaches that wall. Now, take the same flashlight outside, into a vast open field at night, point it upward, into the sky. The same flashlight, with the same brightness, suddenly seems much dimmer. Its light has nothing to bounce off. It spreads outward into the open space, weakening in every direction. The flashlight has not changed. The light has not changed. Only the stage on which the light is being released has grown larger. This is the idea of extra-dimensional gravity. The source has not been weakened. The stage has been widened. And we, living on a 3-dimensional slice of a larger reality, see only the faint local portion of a force that, if you could stand outside our universe and look at it whole, would be just as strong as anything else. If this picture is correct, it would mean something stunning. It would mean that gravity, at very small scales, scales smaller than any experiment has yet probed, should suddenly appear far stronger than we have ever measured. If we could push close enough to 2 objects, into the realm where the curled-up dimensions become accessible, gravity would no longer feel feeble. It would feel as fierce as the other forces. The hierarchy would dissolve. The mystery would melt away. Gravity would only seem weak, because we have never been able to look closely enough to see it whole. Physicists at the Large Hadron Collider, the enormous particle accelerator buried beneath the border of France and Switzerland, have been quietly searching for signs of this for years. They have looked for tiny black holes that might form when particles collide at high enough energies. Black holes that would only be possible if extra dimensions were real and gravity was stronger at short distances than we currently know. So far, they have not found any. The search continues. The idea remains unproven. But the idea remains alive, because no one has been able to rule it out either. Somewhere, in the silence, at the bottom of every atom, there may be entire hidden landscapes through which gravity is freely pouring. That is the first attempt at an answer. Now let us walk to the second. The second idea is quieter, and in some ways stranger. It does not say that gravity is hiding in extra dimensions. It says that gravity, like every other force, is carried by a particle, a messenger. A tiny entity that travels between objects, communicating the gravitational interaction from one place to another. And the reason gravity feels so weak is that this particle, if it exists, interacts with matter so faintly that we may never be able to detect a single one. You have to step back to understand what this even means. In the modern picture of physics, forces are not invisible reaching hands. They are communications. They are messages exchanged between particles. Electromagnetism, for instance, is carried by particles called photons. Every time two electrically charged objects push or pull on each other, photons are flying between them, carrying the message of the force. You cannot usually see these photons. They are invisible to your eyes. But occasionally, when many of them are released together with the right energy, you do see them. The light from your screen right now is a stream of photons being emitted by your device and absorbed by the cells at the back of your eyes. Photons are the messengers of electromagnetism, and we have detected them by the trillions. We have built entire technologies around them. They are real, and we know them well. The strong nuclear force has its own messengers, particles called gluons. They glue the heart of every atom together. They are confined inside the nucleus, but their effects are unmistakable. We have detected them too. The weak nuclear force has its messengers, particles called W bosons and Z bosons. These are heavier and stranger than photons, but they are real, and we have detected them as well. The discovery of the W and Z bosons in the early 1980s was one of the great triumphs of particle physics in the 20th century. So if every other force has a messenger particle, and if our best theories of physics suggest that forces in general should work this way, then gravity should also have a messenger. There should be a particle that carries the gravitational interaction. Physicists have given this hypothetical particle a name. They call it the graviton. The graviton is one of the most quietly haunting particles in modern physics. It has never been detected, not directly, not even indirectly in any conclusive way. It exists, for now, only in equations. And here is the problem. According to the theories that predict the graviton, it should interact with matter so weakly that detecting even a single one would require an instrument larger than anything humans could ever realistically build. Estimates vary, but some calculations suggest you would need a detector roughly the size of the planet Jupiter, made of the densest material in the universe, sitting in orbit around an extremely active source of gravitational signals, and even then it would take longer than the current age of the universe to register a single graviton. Think about that. A particle so faint that you could, in principle, look for it for billions of years and never see one. A particle that, if it is the true carrier of gravity, would explain everything we feel as the cumulative effect of an unimaginable number of these almost invisible messengers, each one delivering a whisper so quiet that no individual whisper could ever be heard. In this picture, gravity feels weak because the gravitons themselves interact with matter so faintly that any single one of them might as well not be there. The reason the entire mass of the Earth is barely enough to glue you to its surface is that the gravitons traveling between you and the Earth are so reluctant to engage with the particles in your body that almost all of them pass right through you, doing nothing. Only a tiny fraction of them deposit any influence at all. The weakness of gravity is, in this view, the weakness of the messenger. The force itself may simply be carried by the most reclusive particle in the entire cosmic family. Is this true? We do not know. The graviton has never been seen. It may never be seen. But its existence is strongly suggested by the mathematical structure of every modern attempt to unify gravity with the other forces. Quantum mechanics, the theory that describes the other three forces with extraordinary precision, predicts that gravity, if it follows similar rules, must be carried by such a particle. So we look, we listen, we build ever more sensitive instruments, and so far, gravity has refused to whisper its secret to us in this particular way. That is the second attempt. Now the third. And the third is the strangest of all. The third idea is that gravity is not a fundamental force at all, that it does not have a deep, primary existence in the structure of reality, that it emerges, like steam rising off a warm cup of tea from something deeper, something more basic, something that we are only just beginning to understand. This idea goes by several names. Some physicists call it emergent gravity. Others call it entropic gravity. The most ambitious versions of it suggest that gravity is not a thing in itself, but a kind of side effect, a statistical consequence of the way information is woven into the fabric of reality. To understand this, you have to take one final strange step. Modern theoretical physics has begun to suspect, over the last few decades, that the deepest layer of reality is not space, not time, not matter, not energy, but information, bits. The most fundamental ingredient of the universe, in this view, is not stuff, it is data. The universe is, at its very lowest level, a vast network of relationships, of connections, of yes and no, of this or that. And out of this network, all the familiar things emerge. Space emerges, time emerges, matter emerges, and in the most surprising of all the recent proposals, gravity also emerges. In this picture, when two objects appear to be attracted to each other, nothing fundamental is reaching between them. There is no force, there is no curvature, there is only the way the underlying information rearranges itself when matter is present. The arrangement of information takes a particular shape near mass, and that shape, from the inside, looks and feels exactly like what we call gravity. The pull is a statistical illusion. The bending is a pattern in the data. The whole edifice of falling apples and orbiting moons and warped spacetime is an emergent feature of something happening at a deeper, more abstract level. If this is true, then asking why gravity is weak is a little like asking why a wave on the ocean is wet. The wave is not wet, the water is wet. The wave is a pattern in the water. Asking about the wetness of the wave is to mistake the surface phenomenon for the underlying thing. In the same way, asking why gravity is so faint may be the wrong question entirely. Gravity may be a pattern. The real question may be about the structure that produces the pattern, the information network, the underlying weave, the level beneath space-time itself. This idea is far from confirmed. Many physicists are skeptical of it. Some find it deeply persuasive. The work continues. The mathematics is hard. The experiments to test it, if any are even possible, lie far in the future. But the very fact that serious physicists are willing to consider that gravity might not be a real fundamental thing tells you how strange the question of its weakness has become. We are not just trying to explain a weak force. We may be trying to explain something that is not even a force at all, but the shadow of a deeper truth we have not yet learned how to read. So there you have it. 3 answers, 3 attempts, none of them proven, none of them ruled out, each one beautiful in its own way, each one pointing toward a different vision of what reality might really be like beneath the surface. Gravity might be hiding in extra dimensions, leaking its true strength into spaces we cannot see. Gravity might be carried by a particle so faint that we may never detect it directly, leaving us to feel only the cumulative whisper of an unimaginable number of invisible messengers. Gravity might not be a thing at all, but an emergent pattern, a statistical echo of something deeper than space and time themselves. The honest answer to why gravity is so weak is, in the year you are listening to this, we do not know. I want to sit with that for a moment, because we live in a time where this kind of admission is rare. Nearly every other voice that reaches you, in every medium you encounter, speaks with certainty. The advertisements are certain, the opinions are certain, the arguments online are certain. Confidence is the currency of attention. To say, "I do not know," in public, is often treated as a weakness. But science does not work that way. Science, at its best, is willing to say, "I do not know." It is one of the few human enterprises in which not knowing is treated not as a failure, but as a starting point. The greatest physicists of our age, the people who have given their lives to understanding the universe, will tell you plainly that the question of gravity's weakness has not been answered. They will tell you their best guesses. They will tell you their favorite theories. But if you press them, the good ones will look at you with quiet honesty and admit that the puzzle is still open. This is not a defeat for science. This is the most truthful part of science. Every answered question began as an unanswered one. Every famous discovery began as a confession of ignorance. Newton did not know why apples fell until he asked. Einstein did not know what gravity really was until he wondered. The people working on the hierarchy problem today, scattered across universities and laboratories around the world, are walking the same kind of path. They are walking it without certainty. They are walking it without guarantees. They are walking it because the question is too beautiful to leave alone. And the most remarkable thing is that the question has changed shape. We started the night with a simple puzzle. Why is gravity so much weaker than the other forces? And we have ended up at a place where physicists are seriously considering that gravity might not really be a force, that space might have more dimensions than we can see, that the fabric of reality itself might be made of information rather than substance. The original question has cracked open into something much vaster, much stranger, much more humbling. This is what real inquiry looks like. You ask a small question, and the answer expands until it threatens to swallow your sense of what the world even is. You started by wondering about gravity, and you ended by wondering about reality. Now, let me bring you back, slowly, gently, to the room you are lying in, to the bed beneath you, to the soft heaviness of your body settling into its place at the bottom of the Earth's space-time hollow. Whatever gravity turns out to be, whether it is a leaking force from hidden dimensions, or the cumulative whisper of unseen particles, or an emergent pattern from a deeper informational fabric, the truth is that you are sitting inside the answer right now. The mystery is not somewhere far away. The mystery is in your weight. It is in the press of the pillow against your head. It is in the way your hand rests where you have placed it, exactly there, without rising or drifting away. You are a participant in the question. The faintness of gravity is not a fact you are reading about. It is a fact you are demonstrating. Every second of your life is a tiny confirmation of the puzzle physicists are still trying to solve. The weakness of the force, or the shape, or the pattern, or whatever it really is the reason you have a body at all. It is the reason your body is not crushed. It is the reason the atoms in your skin and your bones and your blood are able to hold themselves apart, neighbors at a respectful distance, instead of collapsing into a single dense point. If gravity were just a little stronger, none of this would exist. The atoms would buckle, the stars would burn through their fuel in hours instead of billions of years. The planets would never form. There would be no slow, patient unfolding of chemistry into biology into mind. The universe would be quick, violent, and brief. The fact that gravity is so absurdly faint is, in a strange and tender way, the reason there is anything here at all to be tender about. The weakness is the gift. This is where we will leave the deepest mystery. Not solved, not resolved, still open, still waiting. But more beautiful than it was when we began. Because now you know the shape of the question. And you know that some of the brightest minds alive are still standing where you are standing tonight, wondering the same thing. In the final part of the night, we will return to you fully, to your bed, to your breath, to the gentle settling of the world around your body. We will take everything we have learned and let it land softly. And we will see how the faintness of gravity, the very thing that makes it so puzzling, is also the thing that has cradled every moment of your life so far, and will continue to cradle every moment to come. For now, lie still. The mystery is alive. The question is still warm. And the night, like the universe itself, is generous with its silence. So let us come home. Let us come back to where we began. Back to your room. Back to your bed. Back to the soft body that has been listening to all of this, breath after breath, through the long unfolding of the night. You started this journey with a simple assumption. You believed that gravity was strong. You believed that the weight in your shoulders and the heaviness in your legs were proof of some great invisible hand reaching up from beneath the earth and holding you down. You believed, the way nearly every human being who has ever lived has believed, that the force binding you to the planet was one of the most powerful things in the universe. You were wrong, not in a foolish way, not in any way you should regret. You were wrong in the gentle, ordinary way that every human being is wrong about gravity until they sit with the question long enough to see it for what it really is. You were wrong because the truth is harder to see from the inside. You were wrong because the world arranged itself to feel a certain way to you, and that feeling has been so consistent and so reliable that it never gave you any reason to doubt it. Of course, gravity feels strong. It is the only force you cannot ever turn off. It is the only one that follows you everywhere. It is the only one you can never escape, not for a single second of your life. How could something so constant feel anything other than mighty? And yet, now you know that a small magnet can lift an iron nail against the gravitational pull of an entire planet, weighing 6 sextillion tons. You know that gravity is the weakest of all the fundamental forces by ratios so vast that no human mind can fully picture them. You know that what you have felt your whole life as the pull of the earth is not really a pull at all. It is the geometry of space gently nudging your body into the natural valley that the planet has carved into the fabric of reality. You know that the chair beneath you is not holding you up against a force. It is interrupting your fall along a curve. You know that falling is the default. You know that standing still is the strange thing. You know that physicists are still wrestling with why gravity is so faint. You know about extra dimensions, those hidden curls of space where most of gravity's strength may be quietly leaking away. You know about the graviton, the lonely whispered particle that may never be detected, the shy messenger that might be carrying every gravitational interaction in the universe so faintly that not a single one of its quiet voices has ever been heard. You know about emergent gravity, the radical idea that the force you have spent your whole life inside is not even a real thing in itself, but a pattern that rises from a deeper layer of reality woven out of information rather than substance. You know all of this now, and the strange and beautiful thing is that none of it has changed your weight. None of it has lifted your body from the bed. None of it has loosened the press of the pillow against the side of your face, or the gentle warmth of the blanket along the length of your legs. Everything you feel right now is exactly the same as it was when you first lay down tonight. The mattress is still firm beneath your back. The covers are still draped softly across your chest. The small, private warmth of your own body still surrounds you the way it has every night of your life. Nothing in your physical sensation has changed. And yet, everything has changed, because now you know what is really happening. The weight in your shoulders is not a force pressing down. It is the universe quietly noticing your existence and pulling the fabric of reality into a tiny, soft curve around your body. The press of the bed against your back is not the floor stopping a fall caused by some great invisible tug. It is the bed stepping in between you and the natural slope your body would otherwise roll along. The heaviness of your eyelids is not the weight of a force pulling them downward. It is the geometry of your room, the geometry of your planet, the geometry of the entire universe, all woven together at this one tender point of your sleeping face. And the truly extraordinary thing, the thing I want you to carry with you into your dreams tonight, is that all of this is happening because gravity is so weak. Not despite its weakness, because of its weakness. The faintness of gravity is the reason any of this can exist at all. Stay with me for a moment longer, because this is the deepest gift the night has to offer you. Imagine, just for a heartbeat, that gravity was stronger, not enormously stronger, just a little. Imagine the curvature it carves into spacetime were just a fraction sharper. What would happen? The atoms in your body would not survive. The delicate balance that keeps the electrons in their orbits around the nuclei, the tiny dance of attraction and repulsion that holds every particle of you exactly where it needs to be, would begin to collapse. The geometry would pull too hard. The structures that make you possible would buckle inward. There would be no skin. There would be no bone. There would be no breath. The complicated cathedral of your body, built from trillions upon trillions of atoms held at just the right respectful distances from one another, would never have been able to assemble itself in the first place. The stars would not last. The sun that warms the face of the earth, the same sun that has been shining steadily for nearly 5 billion years, and will keep shining for billions more, would burn through its fuel in a matter of moments. The slow, patient fusion of hydrogen into helium, the long, gentle pour of energy that has kept this planet warm enough for life to find its way upward through the long climb of evolution, would have ended before it could begin. A universe with stronger gravity would have no slow stars. It would have only quick, violent flashes that died before any planet around them could cool. There would be no time for life. There would be no time for anything. The planets themselves would not form. The dust and gas that gathered together over millions of years to make worlds like ours would collapse too quickly, too aggressively, crushing themselves into compact, dense lumps long before they could organize into the layered, structured spheres that allow for atmospheres and oceans and breathable air. There would be no soil. There would be no rivers. There would be no trees standing patiently along the sides of quiet roads in the middle of summer afternoons. There would be no afternoons at all. This is what the faintness of gravity has given you: time, space, patience, a universe slow enough and gentle enough that complexity has been able to take root in it. A cosmos in which atoms can hold themselves together long enough to form molecules, in which molecules can hold themselves together long enough to form cells, in which cells can hold themselves together long enough to form the trembling, intricate miracle of a thinking, breathing, sleeping human being. All of this depends on gravity being exactly as weak as it is. A little stronger, and none of it would be here. A little weaker, and the stars would never have formed at all. The matter of the universe would have stayed too diffuse to gather into anything, and the cosmos would be a vast empty wash of thin, cold gas drifting forever in the dark. The weakness is not a flaw. The weakness is the gift. Read that line slowly. The weakness is the gift. The very thing that made gravity feel like a puzzle, the very fact that has driven physicists half mad for a century trying to explain it, is the same fact that has made you possible. The same fact that has made your bed possible. The same fact that has made the trees outside your window possible. The same fact that has made the slow turning of the seasons possible, and the long, quiet history of every face that has ever looked at the sky, and every voice that has ever spoken a kind word in a darkened room. All of it owes its existence to the faintness of the force we once thought was mighty. Without that faintness, the universe would have had no patience. It would have rushed itself. It would have collapsed before it ever knew it was here. Instead, it spread itself out. It moved gently. It gave the matter inside it time to find one another. It let stars burn slowly. It let planets cool slowly. It let chemistry try its small experiments for billions of years until one of them, somewhere on a damp, rocky world orbiting an unremarkable star in an unremarkable galaxy, learned how to copy itself. And from that single trembling beginning, everything else came. Every fern, every fish, every bird, every fox, every grandparent who has ever held a child's hand, every memory you carry, every sound you have ever loved, every word of this night, all of it because gravity was weak enough to let it happen. Now, feel your body again, the whole of it, from the top of your head to the soles of your feet. Feel the way your weight settles into the mattress, distributing itself across the soft surface beneath you. Feel the gentle warmth of the blanket where it touches your skin. Feel your own breath moving in and out, in the slow rhythm that your body knows without being told. Every part of this is gravity doing its quiet work. The way the pillow shapes itself around your head is the geometry of spacetime, gently insisting on its slope. The way the sheets fall in soft folds along the sides of your body is the same. The way your hands rest exactly where you have placed them, not drifting away, not floating upward, is the same. The way the lamp on your nightstand stands obediently in its corner, not tipping over, not rising into the air, is the same. The way the air in your room sits calmly around you, not rushing away into the sky, is the same. Every small reassurance of your environment, every familiar arrangement of objects in their proper places, every steady detail of the world around you is a quiet expression of the same weak, gentle geometry that has cradled your entire life. You have lived inside this geometry from the very first moment you ever existed. The cells of your body assembled themselves within it. The first breath you ever drew was drawn against its quiet pull. The first time you opened your eyes, the room you saw was arranged in the way it was because of it. Every step you have ever taken has been a step along its slope. Every fall you have ever taken has been a roll into its valley. Every hug, every kiss, every careful placing of a hand on a shoulder has been a small act inside its gentle frame. And now, tonight, as the room around you grows quieter and the world outside your window slows down, the same geometry that has held you all your life is holding you still. It is the geometry of your bedroom, the geometry of your house, the geometry of the soft, small corner of the planet where your body has come to rest tonight. The geometry of the earth itself, that vast spinning sphere, has carved this little hollow around you, and you have sunk into it, the way you sink into it every night, without thinking, without asking, without ever having to understand what is really happening. But tonight, you understand a little more. Tonight you know that as you lie here, the planet beneath you is not pulling you downward. Nothing is pulling you. There is no rope, there is no hand, there is no invisible reach. There is only the soft, natural shape of the universe around your body. A shape so gentle that a refrigerator magnet can outshine it. A shape so faint that physicists have spent a century arguing about why it is so quiet. A shape so subtle that, if it were any softer, you would not exist, and if it were any sharper, you would not exist either. The universe has tuned its quietest force to exactly the level required for you to be here, listening to a voice in the dark, feeling the press of your blanket against your chest, slowly letting the day fall away. You are not falling asleep. You are surrendering to the gentle geometry of existence. That is what sleep is in this new picture. You are letting the natural curve of the world take you the rest of the way down. You are allowing the same quiet, faint shape that has held you all night, all your life, all your existence, to finally guide your body into rest. You are not being pulled into your dreams. You are rolling softly along the slope that the planet has carved for you, into the small private valley where your body knows how to rest. And here is the truth I want you to carry into that valley with you tonight. The smallest force in the cosmos is the one tucking you in, not the strong nuclear force with its furious grip on the heart of every atom, Not the electromagnetic force, with its bright crackling reach across every device and every surface. Not the weak nuclear force, with its slow, patient work inside the cores of distant stars. None of those is what is settling your body now. The force that is shaping your night is the faintest one, the weakest one, the runt of the cosmic family, the one that loses to a magnet you could lose between the cushions of your couch. And yet here it is, quietly, without effort, without drama, doing the most tender thing in the universe, cradling you into sleep. This is the picture I want you to fall asleep inside tonight. Not a fact to remember, not a lesson to recite, a feeling, a small sense that the weight in your body is not a weight at all, but a curve carved by a planet, a curve nested inside the larger curves of the solar system, a curve nested inside the still larger curves of the galaxy, a curve nested, ultimately, inside the gentle overall shape of the entire universe. And you, somewhere deep inside all of these layered shapes, are simply resting at the bottom of your own small private hollow, the way every living thing on this planet rests every night. You belong to the geometry. The geometry belongs to you. Neither of you is reaching out to grab the other. You are simply, quietly fitting together, the way you always have, the way you always will. Let your eyelids grow heavier. Let the small distances between your thoughts grow wider. Let the warmth of the bed sink a little deeper into the muscles of your back. The geometry is holding you. The fabric is gently shaped around you. The universe is asking nothing of you tonight, except that you let yourself be where you already are. Tomorrow, the world will look the same as it did yesterday. The coffee in your cup will still sit flat. The water from your tap will still arc downward. Your steps will still land where you expect them to land. From the outside, nothing will have changed. But you will know that every moment of weight you feel from now on is a quiet conversation between your body and the curvature of reality. You will know that the simplest sensations of your daily life, the press of a chair against your back, the heaviness of a grocery bag in your hand, the feel of your foot finding the floor in the morning, are all expressions of the same faint, beautiful, weak, tender force that has been working quietly in the background of every breath you have ever taken. You will know that the universe is far stranger than it appears, and that the strangeness is not somewhere far away. The strangeness is inside the most ordinary moments of your life. The strangeness is in your weight. The strangeness is in your stillness. The strangeness is in the gentle way the world has of holding everything together with the lightest possible touch. And maybe, in the quiet moments of your days to come, you will pause for a heartbeat, and you will feel that weight in your body, and you will remember that what you are feeling is not a force, it is a shape. You will remember that what you are feeling is not strong, it is weak, beyond imagining. You will remember that what you are feeling is not pulling you, it is cradling you. You will remember that the smallest force in the cosmos is the one that has been holding you all along. And then, with that small private knowing folded gently into your chest, you will return to your day, to your work, to your meals, to the faces you love, to the slow, ordinary unfolding of a life lived inside a universe that has tuned itself, in ways we still do not fully understand, to make a place for you to be. For now, though, none of that needs to happen. For now, the day is over. The light is low. The room is quiet. The blanket is warm. The geometry is soft. Let yourself go. Let your body settle into the curve. Let your breath slow. Let your thoughts drift. The earth beneath you is not pulling you down. It is cradling you along the natural shape of the universe itself. You are not falling asleep. You are surrendering to the gentle geometry of existence. The smallest force in the cosmos is the one tucking you in tonight. Sleep well,